Well, hello everyone. Today we continue our lesson on the derivatives of inverse functions. In particular, we will focus on the derivatives of inverse trigonometric functions. Now, here we were given, the last time we were given some rules or facts about the derivatives of inverse trig functions. The first one says the derivative, the sine inverse of x is equal to 1 over root 1 minus x squared. The derivative of cosine inverse of x is equal to negative 1 over root 1 minus x squared. d dx of tan inverse of x is equal to 1 over 1 plus x squared. d dx of cotangent inverse of x is equal to negative 1 over 1 plus x squared. d dx of sine inverse of x is equal to 1 over absolute value of x times square root of x squared minus 1, and d dx of cosecant inverse of x is equal to negative 1 over absolute value of x times the root x squared minus 1. We will now take the time to prove the first one. d dx of the sine inverse of x is equal to 1 over the square root of 1 minus x squared, and the rest we will leave for an exercise for you. So, consider this triangle where we label y as our angle, x as our opposite side, and the hypotenuse of 1. Then by Pythagorean theorem, the adjacent side to angle y would be radical 1 over 1 minus x squared. So in this case, y is equal to sine inverse of x, because the sine of y would be equal to opposite over hypotenuse, which is x over 1, which is equal to x. Also, the sine inverse function lives between negative pi over 2 and pi over 2. This triangle is between 0 and pi over 2. Your angle y, but we're going to prove it for this triangle and then also extend it to say, okay, it will also hold for the negative, from negative pi over 2 to 0, because of the fact if we negate both sides of this answer, then the negative and the negatives cancel. But let us do the derivative of the sine inverse of x. We take the d dx of sine inverse of x. By the theorem of inverse functions, which you learned from the last time, it's going to be a 1. The derivative of the inverse function, in this case, which is sine of x, evaluated at the function that we're looking at, which is a sine inverse of x. So look for whatever is the inverse of sine inverse of x, which is sine of x. And then evaluate it at sine inverse of x. So that is what we get by the theorem. So the derivative of the sine of x would be cosine of x. Derivative of sine of x would be cosine of x. So derivative of sine inverse of x would be the cosine of the sine inverse of x. Now, we know that the sine inverse of x based on our triangle will just be y, because y is equal to sine inverse of x, and that is from the definition on the triangle. And so what we want to do finally is insert the value for cosine of y. And remember, cosine of y was adjacent over hypotenuse, so that's radical 1 minus x squared over 1, which is just radical 1 minus x squared, and we plug that in. So that's going to be equal to 1 over radical 1 minus x squared, because we substitute cosine of y is equal to radical 1 minus x squared from our triangle. So therefore, we have shown that the derivative or the sine inverse of x is equal to 1 over radical 1 minus x squared. And so that is our proof. Now we are going to use the answers or the functions that we're given to do a couple of things. First of all, I want to find the derivative of f of x is equal to 4 cosine inverse of x minus 10 tan inverse of x. So to find f prime of x, what we will do is that we will say f prime of x is equal to 4 times d dx of cosine inverse of x minus 10 d dx tan inverse of x. That was from our constant multiple derivative ideas. And then the derivative of cosine inverse from our table was negative 1 over radical 1 minus x squared. So that's going to be 4 negative 1 over 1 minus x squared, radical 1 minus x squared, minus 10. The derivative of tan inverse was 1 over 1 plus x squared, so that's 10 times 1 over 1 plus x squared. And then we try to simplify that as much as possible. So this answer simplifies to give negative 4 over radical 1 minus x squared minus 10 over 1 plus x squared, and we're done. We go to number 6. We tried to find the derivative of g of x, when g of x is equal to radical x sine inverse of x. Now notice here that this is a product. Notice this is a product. So we're going to apply the product rule as well as the inverse derivative theorem. So g prime of x would be equal to first times the derivative of the second, which is radical x d dx sine inverse of x, plus the second, which is sine inverse of x d dx radical x. Now we could have, like we did previously, rewrite our radical x as our fractional exponent. That was x to the 1/2, and you can do that, and then later on you can reconvert them to radicals. I'm just going to go ahead, since we've met this guy before, just go ahead and just write what is his derivative and then work from that. So this is going to be radical x times 1 over radical 1 minus x squared. That was the derivative of sine inverse of x plus sine inverse of x times 1 over 2 radical x. And then finally, simplifying that as much as possible, we have radical x over radical 1 minus x squared plus sine inverse of x over 2 radical x, and we are done. Next problem, h of x is equal to sine inverse of 2x cubed. Now notice, now this is not just a sine inverse of x. It's sine inverse of 2x cubed. So we're going to have some sort of chain rule thing happening here, because then the derivative of 2x cubed will also come into play. So then by the chain rule, the d dx of sine inverse of 2x cubed is going to be taking the derivative of sine of x, sine inverse of x, which would be at 2x cubed, which would be let's keep this 2x cubed in the correct format. The cube was inside, so let's keep the cube inside. Okay, 1 over radical 1 minus 2x cubed squared times d dx of 2x cubed. So that's going to be equal to 1 over radical 1 minus 2x cubed squared times 6x squared. And then we can bring the 6x squared to the top to finally complete this simplification. So it becomes 6x squared over radical 1 minus parentheses 2x cubed squared, and we're done. If you want to expand that out a little bit further, you can, to make it 6x squared over radical 1 minus 4x to the 6th power. That is fine. Okay, let's look at another problem. Another problem is an application with a position function. The position function was given as the s of t is equal to tan inverse 1 over t, where t is greater than or equal to 1/2. So we want to find our velocity function from this. Recall that the velocity function is the derivative of your position function. So velocity function v of t is equal to s prime of t. And then we have a tan inverse happening here. So then we want to find the derivative of all of this, but it is evaluated at 1 over t. So we're going to have some chain rule thing happening here again, because we have to find the derivative of this 1 over t. So let's see what happens. So it's going to be 1 over 1 plus 1 over t squared times the derivative d dt of 1 over t. And then from our chain rule ideas, let's do this. Let's simplify this a little bit more. 1 over 1 over 1 plus t squared, because 1 over t is going to be 1 squared. That's 1 over t squared. That's t squared. And then the derivative of 1 over t, d dt of 1 over t is going to be negative 1 over t squared. And so we have a bunch of fractions to simplify right here. If we look at this first part, 1 over 1 plus 1 over t squared, it's going to be like 1 over t squared plus 1 over t squared, 1 over t squared plus 1 over t squared. You flip that over because you're taking the reciprocal of that. It's going to be t squared over t squared plus 1. Then multiplying this by negative 1 over t squared, we multiply straight across, and then cancel out stuff. It's probably easier to cancel out stuff here because we see t squared in the numerator and t squared in the denominator. So then our final answer would be equal to negative 1 over t squared plus 1, and we are done. Now, if we wanted to find the velocity at t equals 1, all we have to do is plug in 1 for t in our velocity function. We plug in 1 for t in our velocity function. So then wherever you see t, you'll replace it with 1. So we have a t squared here. We replace it with 1 squared. So that's 1 over 1 squared plus 1. 1 squared is the same as 1. So 1 plus 1, that gives you 2. So v at 1 is equal to 1 over 2. Thank you so very much for watching. See you next lesson.